So I thought I'd spend just a minute talking about the input file. So let me bring it up here. So here's the input file that you've seen in some of the other videos. And in order to talk about the input file, I think we really need to start with KO, the code itself, and have a look at the read statement. So this is a section of the code around line 123. And this is the read statement for inputting the material properties for a given material insert within KO. So you can see here is the line, the read line, and this is a formatted read. So you can see that it's reading two integers that are 7 digits long, 7 scientific notations that are 7 digits long with 3 digits past the decimal place. Here's 3 9-digit scientific notation with 3 decimal places. Here's 10 scientific notations that are 7 digits long, 3 digits past the decimal place. Here's all the variables, right? So if you added these up, 2, 9, 12, 22, there's 22 variables here that are being inputted. So that's what we've got going on here. Here's 22 numbers that describe a material insert within KO. So the next thing to maybe have a look at is this line here. And this line is just a reminder for the user as to what the units are for the numbers below. And the units are listed here in Wilkins' book. This is what, page 20 of Wilkins' book. So we're in megabars, centimeters, microseconds. Not my favorite unit system, but such as it is. So you'll see here megabar, centimeters per microsecond, grams per cc, etc. All right, so the first flag that is red here is this IEOS. And what that is the equation of state for this material. So you can have more than one equation of state. And if you go look on the code on around line 146, this is that's boundary conditions. Let's go to 810. Here's the equations of state here. It's in section 8, which I'll talk about in a different video, the various sections as they're related to the Wilkins book. But you can see here I've listed, what is this, 6 different equations of state. So EOS 1 means meager Nissen, EOS 2 means a gamma law ideal gas, EOS 3 means an ideal gas with Newtonian stress. Here's some snow plows, and then finally there's a EOS 6 means P alpha. So that's what this number here is. This is describing what equation of state to use for this material insert. This next number is the number of nodes. This is the number of Lagrangian nodes to discretize this material with, so 300. The length is 0.3 centimeters. And it starts at minus 0.3, so that means this material is going to run from minus 0.3 to 0 in the x domain. The initial pressure, velocity, and density are listed here. I think that's pretty straightforward. Here are the units that go along with that. Now these are the beginning, these are the initial, that's the initial energy. This is the beginning of the equations of state here. So this rho naught naught has to do with P alpha. So if you're not using the P alpha, which we're not here, we're using meager Nissen, then this will be ignored. C naught and S1 and S2 are the reference Hugonio for the equation of state. C naught is the sound speed or the bulk sound speed. S1 and S2 are the Hugonio slopes respectively. And if you want to look at those, a good source for that is in Wilkins' book. He lists here on table 3.1 all of the various material properties that you need really to run KO. So here's the density in the right units, the bulk sound speed, S, gamma for for the that's the meager Nice gamma. And this K1, K2, K3, it's listed down here. These are kind of old notations. K1, K2, K3 were polynomial variables for the meager Nice equation of state. They're really combinations of S and C in the density. If you want to know what K1, K2, and K3 are, you can look on Wilkins' book on page 62. And if you compare, here is the classic meager Nice equation of state here. And if you compare this with the expansion of this in terms of strain, you see that you end up with this x, which is 1 minus the volume here, expanded out in terms of x being to the third power. And here's K1, K2, K3. So if you just gather these terms up, you can compare these and see what they are. So K1 is rho naught c squared, for example. So that's the bulk modulus. Here's K2, rho naught c squared times 2s minus gamma over 2, and so forth. All right, so if you put in S1, S2, that's the linear and nonlinear terms for the Hugonio, then KO will calculate the K1s, K2s, and K3s within the code. And that's done right here. So if you're interested in looking specifically at a particular equation of state, you can scroll down. So here, for example, is meager Nice 1. Here's the gamma law here. And so you can see here's K1, K2, and K3 being calculated. And all of this really is coming from, again, from Wilkins' book. It's here in the appendix. So if you look in the appendix, you'll see here's the equation of state that's being utilized for meager Nice. All right, so moving on here, we got the gamma. That is also part of the equation of state for meager Nice. Now we're getting into the material properties, the elastic plastic deformation. That's these three. This is the yield, the mu, and the fracture criteria. So you need to know two elastic parameters in order to specify the elastic behavior. And in KO, what's done is you're specifying the shear modulus G, and you're specifying the bulk modulus K. And the bulk modulus K is really specified by C naught squared times the initial density rho naught. And so that'll give you the bulk modulus. And if you think about the elastic parameters, and you go to, say, the wiki page for elastic modulus here, you can look and see here's the relationship between all the elastic parameters. So here's K, the bulk modulus, the modulus of elasticity. Here's your shear modulus. So if you know K and G, then you can calculate any of the other elastic parameters. Here's your Poisson ratio. So that's what's going on there. So we're specifying the elastic behavior with this mu, the shear stress, and then here's the plastic behavior. The flow stress is at 3 megabar. So the elastic is mu, which is G, and then the bulk modulus, C naught squared times rho, and then the plasticity starts at the yield strength. This P-frac, you can look in the book, there's a good description of what P-frac is, but it's basically in tension the material fails and actually pulls apart, so the nodes are broken. The connection between Lagrangian nodes is disconnected if you exceed this P-frac. In general, the SPAL part of the code works quite well, but you need to be careful when you run it because of this material breaking apart the connection between Lagrangian nodes. This is our connection to the equation of state. This is the specific heat in units of megabar cc grams Kelvin. And then these are the alpha parameters associated with P alpha equation of state. So if you look in the original P alpha paper, then you'll find these parameters.
So it's important to recognize that because this is a formatted read in Fortran, and maybe one day I'll fix this, that you are careful not to violate this formatted statement here. So what that means is that where the numbers are within ko.in are not arbitrary. So for example, the first variable that it's going to read is this IEOS, and it's expecting to see that in the first 7 characters formatted as an integer. So if I go down here and I highlight this, right, look at where my cursor is, it's there. So if I count over 1, 2, 3, 4, 5, 6, 7. So that represents IEOS right here, these first 7 characters. The next 7 characters are going to be the J1 variable. So that is the number of nodes. So that's this 1, 2, 3, 4, 5, 6, 7. So again, it's that blue 7 digits, and it can't be 6, it's got to be 7, right? And 8 is way out. The next one here is 7, there's going to be 7 of these scientific notations, all 7 characters long. So again, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there's 3 numbers in a row. Notice they don't have to be scientific notation input, but they can be. But they have to only be the only numbers that are in those 7 spaces. And so this line right here is helpful because the last character of each of these variables is the last location that it marks the end of that read for that particular variable. So in other words, iStart has to end here and be 7 long. Row not has to end right here at the 0 and be 7 long in front of it. And so if you just are careful and line up all of your numbers with the name above it and be sure not to exceed the previous variable space, then your read should be just fine. If you violate this, you're going to get all kinds of problems. Also, don't use tabs within any kind of text file in Fortran.
Okay, the next thing to have a look at is the boundary conditions within KO. So I think I'll take you to this section of the code around line 461. This also shows the boundary conditions. Here's the implementation of the boundary conditions within the code. If you look at Wilkins' book, down here in the appendix, he describes the boundary conditions here, B3, page 195. So here's how he discretizes the boundary conditions. That was just simply a free surface. And so that's the simplest one that I implemented. And that is shown here in the code, the free surface and a stress-free end. So that's a 1. So that means the far left side of the code, which is denoted by the boundary -1, the 1 corresponds to the free end, and the minus sign corresponds to the left side of the computational domain. So here on the line below, the positive 1, I end, means that it's the right side of the computational domain. And the 1, again, means a free surface. So I also put in part of the contact check. So if you think about what you would need for a contact check, you would need internal free surfaces within the one-dimensional discretization. So a -1 and a -2 represent the, a -2 and a +2 represent free surfaces within the computational domain. And then a 4 is a fixed end. I think I've also implemented some other boundary conditions within the code, and feel free to input your own. And when you look at this, it's pretty easy to follow. So here's where it's doing a -1 boundary condition. Here's where it's calculating the phi, the beta, and the u, and that comes right off of this page here, the phi, the beta, and eventually the velocity for that interface. Some of the boundary conditions require that you specify the pressure, the velocity, the density, the energy, and the volume at the interface. So that's why these other variables exist. If you're just using 1 or -1, then you don't really need any other parameters here. These will be ignored. And the same goes up here. If you're using 1, which is the Meagher-Neison equation of state, then it's going to ignore, the code will ignore what you put in here for the alpha terms, which is why I've set them all to 0. The last thing in the code is the t-stop in microseconds 154. That's really just how many microseconds to run the code. And then the code, once it sees this line, stops reading the input file. It'll read as many of these lines as you put. So you can put as many materials in there as you want. You don't just need 2 materials. You could put in, 10 or so. But you'll only ever put in 2 boundary conditions and 1 t-stop. So sometimes I store other materials down here. This looks like it's copper maybe, 8.93 density, just so I don't have to retype them in all the time. All right, so that's a quick tutorial on the KO input file and how it's connected to Wilkins code and the fortran code itself. Hope you enjoyed it. Thanks.